what can we do on this? What's the first thing we notice? Anything raised to a 0 power is 1, so that whole thing just means times 1, so we don't need it there anyway. Love it. What else can we do? And we can kind of work this at the same time. Be super careful, because what do we need to do first? Yeah, we need to square both of these pieces. So we need to have 2 squared and y squared squared. So our numerator is going to be our 3y cubed, and then our 2y squared times 2y squared, or 2 squared, 4y to the 4th, because we have our 2 squared and our y squared times 2. That's how we do those. They both get the power. How about our denominator? It's going to have y to the what? Y to the 4th to the 3rd. So when we take our powers to powers, what do we do with those two numbers? Multiply them. So we're going to have y to the 12th. Do I need to write bigger? A little bigger. Let me make my marker just a smidge bigger. 6. There we go. All right. I'm going to go sideways just so that I don't wind up at the very bottom of the screen, because it makes it really hard to see at the bottom or at the back. So now we can combine things together. Once we have all of the exponents dealt with on the outside of those parentheses, now we can start combining things together. So what number are we going to have in our numerator now? 12, because we have our 3 times our 4, so we're going to have 12. How many y's are in our numerator altogether? 7, because we have y to the 3rd and y to the 4th. So we have y to the 7th on the top over y to the 12th. Which means our answer here is going to be what? When we finish simplifying this, 12 over y to the, and we do 12 minus 7, because we're going to have 7 of them that cancel out, which would be to the 5th. So we should wind up with 12 over y to the 5th. Cool. Okay. It has lots of little pieces, but just work them individually as we can. Any other ones that we were kind of sticking on? Yes, sir. 38 on 1.2? You said 38? Okay, cool. Let's look at 38. Ah! Oh, that's why. Ah! Sorry. My thing's being weird. Just going to erase that. There we go. Ah! There we go. All right, so then let's look at 1.2, number 38. And 38, that one is our black. We've got 25z to the 4th to the minus 3 over 2. Yeah, that one's weird. There's lots of pieces there. So, first things first, what does a negative exponent do? Inverts it. It flips it, puts it as a reciprocal. So, the very first thing I'm going to do is deal with that negative exponent. So, I'm going to make this be 1 over my 25z to the 4th to the 3 halves. So, we can make that negative exponent go away by putting it into a fraction. Totally valid. Thinking through this exponent down here, that 3 over 2, what does that mean? What are we going to do with that? Kind of gross. It's the square root of that chunk cubed, right? Because our denominator here, this is our index. So we're going to take a root with an index of 2. So we're going to have our 1 over, and we can take and do our index of 2 with our 25z to the 4th. And then I'm going to put on the outside our cube. Now, you can do the cube first if you want to, but since I saw we were doing a square root and I saw a 25, I'm like, ooh, square root first. We like that. Square roots and 25s we like, because what is the square root of 25? 5. What is the square root of z to the 4th? Z to the 2nd. So we can actually get this, like, we can take the perfect square. I'm going this way again. So we're going to have our 1 over, and if I take the square root of 25, we have 5. Square root of z to the 4th is z squared. And then we still have our cube out here. So we take our fractional exponent and break it into its pieces, and then we can order of operations this thing. Because now we need to cube our denominator, and then we are done. Can I get one more? I can get one more. So we have our 1 over, what is 5z squared cubed? 125, because 5 times 5 times 5, 5 cubed. And z squared times z squared times z squared, which is z to the 6. I always put a little cross on my z simply because from my handwriting, my z's and my 2's wind up looking too dang on similar. It's the only reason I cross them. But that's why I write my z's here, because if I write my 2's fast, they don't get the loop and they look like z's. So that's the only reason I do that. It's the same reason I do it with my 7's. Yes, dear?
Is it okay if I did it differently without saying answer?
Totally fine. There are lots of different orders in which we can do things. If you're ever not sure if the way you took or the pathway through that you got to somewhere is right, or if we just like happen to make mistakes that cancel it out, let me know. I can always take a look at it for you. But I just tend to take either the path that we are talking about as we're going through it, or what I have seen as the most common pathway. But that doesn't mean it's the rightest. It just means it's what I see. Okay. Any others real quick? Yes, dear.
28 for 1.2.
28. Let's look at 28. Number 28, which is, ooh, wide. So that one is our 2x squared y to the minus 5. That one?
Yep.
Okay, cool. I just like to double check because for some reason there's like 4 questions in the book that are randomly different. So if I ever like start doing a problem or post an answer for something that you go, that is not the same problem, please let me know, because I have no idea which problems, where, or why. But there's like 6 problems throughout the whole course that just don't match randomly in some books. Love it. It's super fun. All right. What the heck are we gonna do? I was gonna say, everything in here is being multiplied together. So I see a couple of negative exponents. So let's see if we can get things kind of situated in a way that I don't have a whole lot of parentheses and we're set up in our fraction. So is the 2 going to go in the numerator or the denominator? Numerator is the x squared, numerator, denominator. Numerator is the y to the 5th, going to go numerator, denominator. Denominator, that's the kind of vibe. I'm just going to kind of split them up like that. So we're going to have our 6 on the top. Blink. Are we back? We're back. Maybe. See, my screen likes to make choices and play games and do all kinds of fun stuff. So if it does a weird and it doesn't fix itself, let me know if I don't notice it. So our 6 is in the numerator because it's got a positive exponent. Our x to the 3rd is in the denominator because it's negative. Then our y in the top. Our 1/3, I could put the 1/3 up here, but that's being weird because I have a fraction and that's unpleasant. So instead of putting the 1/3 in the numerator, I'm just going to put the 3 in the denominator because it's 1/3. It's just like having a 1 here, 1/3. And then we have our x to the 1st down here and our y cubed up here. So everything's being multiplied together, so I do not need my parentheses. But if you set this up as separate fractions and then multiply, that's totally okay. That's just where my parentheses would be. So like that's totally fine. It's the same thing as if I wrote them as separate fractions and smashed them together. I'm going to get rid of those parentheses because they hurt my heart. So then let's simplify this because that is a chaotic mess of chaos. And if you do this in fewer steps than me, that is okay. Like if you do this and it takes you like 2 steps, cool, love it. I just tend to write a lot of steps. So we can combine things together in here. I've got my 2 and my 6. We can multiply those together to get our 12. I've got my x squared, and I have y times y cubed. That's going to give us a y to the 4th. That's my numerator here. And then simplifying my denominator, we have our 3. X cubed times x gives me x to the 4th and y to the 5th. So that's what lets us look at this and kind of simplify. When in doubt, when you're simplifying, look at each piece individually. Look at your just the numbers, then look at our just x's, then look at our just y's. So if you struggle looking at things like this on how to simplify them, look at them as pieces. Because if we simplify just the numbers, 12 over 3, good? 4. What are we going to be left with for our x's? X squared on the bottom.
And then just 1 y.
And then just 1 y on the bottom. And that's our answer. 4 over x squared y. Okay. So do your numbers, then your x's, then your y's. Cool, cool? Feel a little better? Yes, dear. 74. Yeah, one of the root ones. And then that's, there we go. Now it's going to let me do that. How's if I'm in the right settings for the page? Ooh. There we go. Okay. 74. So let's look at that one. 74. That one has our 5th root of a fraction. That has our 3x to the 11th y cubed over 9x squared. All right, and this is one that we're going to simplify and then rationalize. So let's start by simplifying the fraction first inside the radical before we try and get things rationalized. You can do it in either order, but I feel like this is going to be kind of the easier way, but it's okay if it's not. So let's see if we can simplify the fraction part first. So we're going to ignore the radical for a second. We can just simplify the fraction part. I'm just trying to make it so we can see that part. So what can we do to simplify that fraction? Yeah, the 3 and the 9, we can simplify that. We're just going to have a 3 in our denominator. What's going to go on with my x's? Yeah. So instead of having x to the 11th over x squared, we're going to have x to the 9th up here. And then we have our y cubed. So we can simplify the fraction first. We still have our 5th root on it. But we're just simplifying the fraction first. That actually is going to get the x's out of our denominator. You can absolutely do this and just straight up split your root here and then rationalize and then simplify. That is also fine. You can do it in whatever order you want. Yes, dear?
Can you just take it to the 5th power to eliminate the rational sign, or would that?
Only if we could do the same thing on both sides and equal sign. Since we have an expression here, and I can't do it to like the other side of an equal sign, I can't just like square both sides, because we'd have to have both sides. So I understand the thought process on that. When we get around to playing with functions that have roots in them, we'll do exactly that. But no, on this one, since we don't have an equal sign, unfortunately, we cannot. But what we can do now to try and rationalize this is we're going to take and split our 5th root of x to the 9th y cubed and our 5th root of 3. That is mostly simplified. I'm going to go ahead and rationalize our root and then finish simplifying our numerator. If you want to simplify or like simplify out our variables here, that's totally fine. Again, you can do things in a lot of different orders. we want to multiply this by something that is going to be a fifth root of something that's going to let me get rid of that 3 in the denominator. We have 1 3. I need to have groups of 5 to be able to get rid of a fifth root. So I need 4 more 3's. So we're going to multiply this by the fifth root of 3 to the 4th. Because that'll give me 5, and that'll cancel out that root. But I can't just multiply by that really weird, super gross decimally number. But I can multiply by a weird looking 1. It is a weird looking 1. Definitely. But it's just a 1. So what we're going to have here, let's do an arrow over here. We're going to have our fifth root of, we have our 3 to the 4th, x to the 9th, y to the 3rd. And our denominator, we're going to have our fifth root of 3 to the 5th. Fifth root of 3 to the 5th is just 3. It's the whole point, is to get that denominator to be a whole number. Yep. Sorry, I'm just trying to make it so that my words are not tiny. So we have one last step to simplify this. With our variables, we have one that can come out of the root. What's going to come out? An x, because I have 9 x's inside. I can take out groups of 5. So we have an x outside. And then we're going to have our fifth root of, we need 3 to the 4th. What is 3 to the 4th? 81. How many x's do we have left inside? 4. And then we have our y cubed all over 3. Okay. That's my white out. Is it all of it over those now? Okay. Let's move forward and look at the next thing we're going to talk about. Cool? Because we are going to talk about polynomials for a little bit. So before we start going too deep into polynomials, we need to remember some things about polynomials. I need to fix this thing in here before I forget that it's there. Yes, dear?
After class, can you go back to that?
Absolutely.
Didn't get finished.
Putting that there so I don't forget. Okay. So we're going to talk about monomials and polynomials and that kind of vibe. So we got to remember these words. So a collection of variables and constants on which operations are performed are algebraic expressions. Pretty much what that means is it doesn't have an equal sign. I'm going to fix it so it doesn't have that black bar at the top. There we go. So I'm going to write these kind of definitions with you. So we've got monomials. Mono. A lot of times it's one thing. So a monomial, which is going to be our longest definition that we write based off of these, is an expression of the form. So it just means it's going to most of the time look like ax to the n. So it'll look like that as long as a is real, so no imaginary numbers. We love that. And n is not negative. Very, very rarely will we get one that has a 0 in it when we're talking about monomials and polynomials, but it could. Huh?
It's just and like and. It's not and.
Oh, there we go. And. I was going to be like,
Don't worry. It took me a while because me and my mother were talking about Jeopardy, and I'm so confused about what she was talking about. She said they give you the answer, they have to answer with it. They have to say the question, and I'm like, I could not comprehend.
Yeah, Jeopardy's weird.
I got some of the answers right though last night.
Good. All right. So monomials are the pieces from which all these other things are made. So important with monomials is that they're multiplied together. So it's a number times a letter to an exponent. And it may or may not have more than one variable. Like it could be ax to the third, y to the fifth. Like that would still count as a monomial. It doesn't just have to be one variable. More often than not, it will be one variable, just because they're really complicated to solve when they're not. But that's what that is. And so we have a couple that have special names for them. We've got binomials, which just means I take binomial, bicycle. That's kind of fun. Two. It's got two different pieces that are added or subtracted together. So it is a sum or difference. I'm just not going to fit it in there. Of 2 must be exactly 2 monomials. So a binomial is made of 2 monomials. X squared plus 4. Y squared plus x squared. 3x squared plus 4y cubed. Those would all count as binomials. They can have addition or subtraction. Either way. So if a binomial is the sum of 2 monomials, a trinomial, tricycle, is a sum of 3. Oh my gosh. Weird Latin roots. What? A sum of exactly 3 monomials.
Both of these can be or differences.
Or differences, correct. Because what that would be is just if it has a negative number in front. So if like your a is negative 2, that would be the same as saying plus negative 2x. So if binomial is the sum of 2 and a trinomial is the sum of 3, polynomial, many. It's any other than 2 or 3. We don't have special names for like a quadrinomial or a pentanomial. Like you could octanomial. You could, but nobody does.
That sounds.
It sounds weird. It sounds wrong. It's not wrong. It's just not used. Nobody uses that. So polynomial is anything other of many monomials. And I'm not going to have you, like, you're not going to need to, like, tell me the exact definition of a polynomial. We're going to work with polynomials. We need to be able to, if I say, all right, let's look at the binomial, know what that means. Look at the trinomial, know what that means. We are going to need to know our degree and our leading coefficient. So these are important pieces of these. The degree of a polynomial, heard it. It's the largest exponent. The largest exponent on a monomial that is specific to single variable. So if it's just like x's, just y's, that kind of vibe, we're not going to deal with more than one variable in polynomials and finding degree. So like, don't worry about that part. Just to be clear. So it is the highest number of any monomial in a polynomial. So the largest exponent. And our leading coefficient is, I'm just trying to find a different color here. There we go. The number a, so just like how this guy, that number, from in front of your highest degree term. We will practice looking at these in just a second. So our degree comes from the biggest exponent of any of our terms. Term is oftentimes what we'll call the monomial. So the biggest exponent of any term, and the leading coefficient is the number in front of it. They're not always going to give us our problems in biggest to smallest order, so sometimes we're going to have to look around and look closer. So we're going to look at a couple of polynomials here. Before we do any of the operations on them, we'll do a what is our degree, what is our leading coefficient thing on it, okay? So I'm going to put two sums of polynomials up here, but we're going to talk about these for a second first. I'm going to change the view so we can see things better. Yes, dear? Say it again. Yeah, give me just 1 second. All right, we're going to look at these ones first.
It's only been 4 days, and I'm already having my calendar from last year where I was writing when my pencil slips on my finger. It's
And
already back.
it's back. I would say mine never left, so. But I also had a summer school class, so. All right. So we've got here a polynomial and a trinomial. On our polynomial here, which is because it's got 1, 2, 3, 4 terms. What is the degree of this piece going to be? 3. It's our biggest exponent. So this polynomial has a degree of 3 because it has the biggest exponent here, which means the leading coefficient, that's not the pen I wanted, is the number in front of that term. So what is our leading coefficient here? 1. On our trinomial over here, what is our degree? 3. Again, this one has the cube as the highest power. It is our biggest exponent. So that's the piece that tells us. So what's our leading coefficient? 4. Leading coefficient. Yeah, no, please feel free to ask me if I abbreviate something. Most of the time it's because I'm lazy. Okay, so degree is your highest exponent, leading coefficient is the number in front of it. So let's look at our adding and subtracting here. So if we are adding polynomials together, I'm going to erase those two pieces. What can we do to add these two things together? Yeah, it's combining like terms. We've got x cubed plus 4x cubed. 5x cubed. And we've got 2x squared plus negative 5x squared.
Negative 3x.
Negative 3x squared.
Why did it?
Okay. And then we have our minus 5x plus no x's. Just minus 5x. It doesn't change. And then our last piece up here, we've got our 7 plus 3. 10. Adding our polynomials, we're combining like terms. So you don't have to do the degree and leading coefficient thing. I just wanted us to practice that for a second. Because now we're going to take some very similar polynomials. Let's look over here at this one. I'll give you a second to write it down. And we're going to subtract these polynomials. You can do this in a couple of ways. You can either do it very similar to the way we just did, where we worked it from left to right and we just did each term individually, or you can distribute the minus sign through. Both ways are totally fine. So you can absolutely do it just by taking each chunk, or you can distribute. It does not matter to me. But we've got our 4x cubed minus 3x cubed. So that's going to give us 1x cubed. I have nothing minus 2x squared. So be careful with that because we have 0x squareds minus 2x squareds, which means we're going to have negative 2x squared. There we go. because he didn't have anything to subtract from, so we just got to be careful there. Then we have our 5x minus 4x, which is just going to give us a 1x. And then minus 3 minus minus 3.
0.
0. Just be careful. So if you choose to do it this way without distributing, you can wind up with like a triple minus situation like we have there. So you can put plus 0 if you want to. You do not need to. It's the exact same thing as not having anything there.
It says knock like you mean it, Jesus.
You gotta knock louder, dude. I'm old. When you whisper knock, I can't hear it.
That's why you do the FBI knock.
Mm-hmm.
Did I tell you when I scared someone in my English class when I knocked so hard?
It happens. Okay. So our adding and subtracting, very, very similar. We're going to do 2 more very, very short ones, and that'll be it, okay? Because we'll remember how to multiply, which you guys know how to do.
Yeah.
Couple of different options on how to multiply. You can box it. You can distribute it. You can do it in your head. If you are a box stand, box away.
I love boxes.
You can box all you want. We just need to be careful. So you can distribute, you can box, you can do whatever you want to. I tend to, when I'm doing things on the board, do distribution simply because it occupies less space when we're doing notes and things. So I tend to do distribution, but if you are a box stand, you can box to your little heart's content. Okay, so when we are multiplying polynomials, we just need to make sure we get all of our terms multiplied against all the other terms. So I'm going to do this as a distribution kind of problem. So I'm going to take my 4x times 3x first, giving us a 12x squared. Then I'm going to take my 4x times the minus 2. And 4x times minus 2 gives us a minus 8x. So I've taken my 4x times both pieces in the second. Then I need to take the 5 times the 3x.
Are we solving for the x's?
We are not, because we don't actually have an equals to on this, so we don't have a way to get a solution. We just have an expression here. So we're not solving it, we're just manipulating it around. We've got our 15x, and we've got our 5 times the minus 2, giving us a minus 10. And then we're going to combine our like terms to get our answer. Because right now we have this written as a polynomial, but we can do this as a trinomial because we have some like terms. We're going to wind up here with our 12x squared. Our minus 8x plus 15x is going to give us a positive 7x minus 10. All right. Okay. Familiar. I was like, this is 100% review. Let's think about this one on the right, because honestly, I get a lot of people that make a mistake on this one. Because we will not wind up with a binomial. This is not 9x squared minus plus 49. Because what it means for it to be squared is to multiply against itself. This is the same thing as minus 3x minus 7 times minus 3x minus 7. Do not tell me it's 9x squared plus 49. There's a middle piece. Okay, after that, you can box, you can distribute, whatever floats your boat. Because you should wind up with a middle term here, because we are going to get our 9x squared that we expected here. But then we have our minus 3x times minus 7, giving us a plus 21x. Minus 7 times minus 3, giving us plus 21x. And then we get our plus 49. So there's a middle term here. So it's super duper important that we do not just think about distributing your power, because that's not how that works. It is being squared, meaning it's multiplying against itself. So that's our answer for that one. Okay. Tomorrow we're going to work more with polynomials. We're going to multiply two trinomials together. We'll talk some dividing. We might start talking about some factoring stuff too. We'll see. So I'm going to put this one up here. We've got homework 1-1, which is technically due today. Homework 1-2 is due tomorrow, and I've got the numbers up there.
Can you go to the page with
Yes. I'm going to put the questions that we asked today back up here.
the, thank you.
Yeah, these are the same ones. They just have more time writing. I can always put the pages back up.